welcome everyone to today's Bite-Size Talk. And I'm very glad to have here Diego Alvarez from the University of Magallanes. And he's going to talk about one of our first-ish NF Core pipelines, NF Core Mag, which is now in version 5. And actually at this moment, I've seen that we have even version 5.1 since yesterday.
Yeah,
So congratulations on that. And with that, I'll give the microphone to you.
thank you, Francisca, for the introduction. Well, my name is Diego, and I'm going to talk about the most recent developments on Mag. Mag is the NF Core pipeline focusing metagenome assembly. And I want to start with a little context of what is this metagenome assembly and what is important. So, if you have a complex sample, either environmental or clinical, you could have several microorganisms there, and each of those have its own genome. If you want to know what is in your sample, probably you don't need a complete genome. You need a target gene like 16S or another one. But if you want to study the properties or the characteristics of this organism, for example, if they have properties to, I don't know, antibiotics, plastic degradation, or among others, you could need the complete genome for that. The problem with that is that the current sequencing technologies are not able to completely sequence a complete genome from one go. Even long-read technologies like nanopore or PyBio can only sequence probably viral genomes from complete, but not bacterial genomes. So when you sequence a genome by shotgun sequencing, you basically have a lot of reads. It could be short if you use Illumina and a bit longer if you use Nanopore. And the first step you need to do is basically try to join them into longer reads by a process called assembly. And this process try to find overlapping region between reads and create more complete reads or more longer reads than the original ones. Also, normally correcting errors and among other things. These longer reads are called contigs, and these normally still don't represent a complete genome. It's very difficult to have one complete genome from after assembly. So the next step is compare these contigs and try to determine if they come from the same genome. This process is called binding. And this binding don't work obviously with overlapping region because this context should not have more overlapping regions between them, and instead uses another techniques like, for example, GC content, gamer composition, and other techniques, and then decides that one or several contexts are from the same genome, and these form the beans, and they are also called MAGs, from metagenome assembled genomes. And these finally are the most complete approximation of a genome you can have in a metagenome assembly. If you need a more complete one, you probably need to do the sequencing on an isolate. But we can work with those depending on the quality of them. So a bit of history first. Mag, as Francisca said, was one of the first pipelines of NF Core. Originally, it was developed by Adrien Goulet, and the first release was in 2019. And from that point, it has been evolving, adding new tools, new features, etc. And the people have also been changing. Right now, we are 5 maintainers. Of course, James is leading the development here, but we also have Jim Downey, Daniel Straub, Adam Rosenbaum, and me. And over the last year or 2 years, we have been accumulating a lot of features. That's why in this year alone, we have 2 major releases, one in May and the other in September. The May one had a lot of breaking change that need to be done before the 5.0 that has the most important features. And obviously, in the NFQ community, we have a lot of other contribution that helps with fixing bugs, adding small features, etc. So obviously, thanks to them and obviously the previous maintainers as well. So in these years, we have been adding several tools and features, but probably the most awaited feature of that have been requested a lot was supporting long read-only assembly that finally has been added in 5.0. This using fly and meta MDBG as options for the assembly. And also, aside from that, we have been adding several tools. These are probably the most important ones. So, new binaries, that is Concord, quality checking gene tools, check-in, check-in2, some tools for non-bacterial genomes, like viral and eukaryotic, and be known for the normalization for short reads. We also have been updated basically every tool used by the pipeline, also the databases, especially important in the taxonomy classification. And we also decided to remove a part that was originally in the pipeline. This was the raw read taxonomy profiling. This is basically comparing the reads against a database, but without assembling them. And this was often could be useful to determine if there is contamination in your sample. But it's what a half-baked solution, and we decided to remove them and instead tell the users to use NF Core Task Profiler that does the same and better. And also we have a release yesterday, the 5.1.0, that is called Platinum Voodoo, that comes with a new binary that is coming, improvements in the documentation, and several bug fixes. Aside from the new features of each release, we have been doing a lot of work on refactoring. Originally, this pipeline was not designed in a very modular way and used a lot of local models that we have been porting to NF Core ones. Obviously, or either adding new NF Core ones or adapting the existing ones into the pipeline. And this has been a lot of work and a lot of changes. From 3.0 to 5.0, we have been 1,000 commits and over 50,000 additions and 10,000 deletions. But we are getting there. We still have some models we have to we plan to migrate to NF Core official models. And we have obviously using some workflows to make the design of the pipeline more modular. This was back 4.0 before the the feature of long-only long-only assembly. And the big problem with this was we have support for long reads, but only for hybrid assembly. So we support either short read only assembly or hybrid with long reads. And the problem is that we have this very tight bounded. So basically, the long reads only were used as a support input, and they were optional. And we have to do a lot of changes here to really support long read only assembly. And this was performed with by Adam. He was the big architect behind this big change, and this PR was a really big one, over almost 100 commits, 5,000 new lines, 6 months of development, and over 200 comments to accomplish this. It was basically a complete rebuild of the preprocessing and assembly workflow to really separate the two inputs, and obviously adding new tools specific for long reads. There were already some tools for that, especially for quality checking, but we have to add new ones. And obviously, new parameters to control how long reads are used in the pipeline. Yeah. So after this, we got the 5.0. Well, this is 5.1. That is almost the same, but with a combi. And we also updated the metro diagram to represent the how the flow of the inputs are now works. I'm going to go in detail of each of these parts. Starting, we have the preprocessing model separated for short reads and long reads. Each of one have its own set of tools to perform the preprocessing. That is the quality checking, training adapters, and in the case of short reads, we have the BB norm step that is can be used to reduce the coverage of the metagenomes to speed up the assembly, but in theory not affecting the quality of the assemblies itself. And for long reads, we have quality checking with nanoplot, nanoq, and chopper, and also adapter removal, etc. Next, we have the assembly itself. So we can do the assembly in either three options possible. We can assemble only short read mode with the spades and a heat. If we also have long reads in the same sample, we can do hybrid assembly with spades also, but in hybrid mode. And for long reads only, we have fly and MetaMDBG. After this, we do the quality checking, basic quality checking with Quast, and prediction of genes with prodigal and genome ID for viral sequences. And then we calculate the coverage or the depth of these means in using bow type. And Minimap for long reads. Then we have a small model for ancient DNA identification that has a set of tools, PyDamage, Freebase, and BCF tools. And after here, we have our assemblies. So the next step is by using binding algorithm to have the max. So we can run one or multiple of the binders. That is metabat, maxfin, concoct, and combine. And then optionally we have Tiara that is used for eukaryotic genome sequences identification. And then also optionally we can have beam refinement that is performed by DAS tool. And this basically takes the output of each of the binaries we run and try to combine, make corrections and combine them to produce supposedly higher quality beans. The binding process is not perfect, obviously. So this tool try to compare different strategies and combine to produce a better output itself. And after we have the final beans for that, we perform the bean quality evaluation with Quast again, and with a specialized tool like Bosco, Shekem2 that give us a completion and a contamination score for each bean. Bosco and Shekem works with databases of genes that can be found in the genome itself. There are orthogonal genes, so basically count them and determine if the genome is complete or not, and it has contamination from other genomes itself. We also have Shenken2 that basically does the same, but uses another approach based in machine learning. Instead of using a database with each of the genes, use machine learning with a model to determine the completeness and contamination. And for taxonomic identification, we have GTDK that use the GTDB database, and we also have CAT as two alternatives. And for gene annotation, we have Broca and MetaU for for eukaryotic sequences. And finally, I don't have that here, but we merged all together in a nice multi-QC report with all the main findings, and also provide the final files for everything. So one of the things that has changed a little is also how the sample sheet works. The command to run Mac5 is basically the same. And the sample sheet has some new fields, especially this last one that is short read platform and long read platform that use internally to determine with what parameters to run the tools, when, especially in the case of long reads, when performing assembly. Because Oxford nanopore reads and PacBio reads have different level of errors. So we can have samples with mixed short plus long reads, like in the first example, where we provide the both files for short reads and also a file for long reads. And if you don't have that and have link long read only, here is a second example where we have only the fields for long reads, And we also have here the an additional parameter that can be used for each multiple runs that, of the same sample. And for short reads, it should be basically the same as the last one, but obviously with the short reads fields instead of the long read ones. What's next in our list of change? We have a lot of issues with requests for new tools and improvements to the pipeline, but this is what have been planned and in progress. So the next one is another binder that is called meta binder. This is on review already. And we also have in review using multiple BinQC tools at the same time, because right now in the pipeline you can only run one of the three we have available. And with this change, we can run the three of them if you want to, and compare the results. Another change that is in progress right now is Big Mac compatibility. And we also have been integrating new tools to simplify both the contamination and abundance. In the case of the contamination, is hostile the tool for that. That should replace the custom models we have right now for using bowtie and minimap in a single tool. And coherent in the case of abundance, that is similar in the sense that they also should replace custom models using minimap and bowtie. And we also have a plan right now at Hackathon complete the NFT suite, because we migrated our test to NFTs, but only have snapshots from one, I guess, or two profiles, and we have to do the other ones. There are 5 or 6 of them, and we will try to complete them now. And thank you for this space to talk about the Mac new features. And if you have questions, suggestions, and issues, you can reach us in the Slack, the GitHub repository, and you can also read the documentation in the core official website.
Thank you so much. That was a great talk. And I am impressed by all the work that has been done by you and your colleagues. With that, we're also open for any questions from the audience. So you can unmute yourself now, or you can write in the chat, and I will read it out for you. And while I leave the audience to think about that, I actually have a question myself. I have not ever run Mac myself, so I was wondering how long is the runtime, and how long is the runtime for the different modes, like for short reads, for mixed run, or for long reads, and is there even a difference?
Oh, it depends. It depends on how much data that you have, and also if you perform co-assembly. We have an option to perform if you have multiple samples from a same place, for example, 2 or 3 of them, you can combine them and assemble all them together. And the runtime for that could be several days or even weeks. But for single samples, I guess the runtime should be around 1 day, maybe, the full pipeline. I have tried that with, I don't know, like 10 samples, and it's about 1 day, 2 days max.
Okay, and there's no difference if you start with long or with short reads?
Long reads should be a little more fast, but I'm not sure how much.
Okay, because that was the other question. How much assembly is actually needed for long reads? Because they can be like already in context, right?
Yeah, in general, long read assembly should be easier because the contexts are the reads, original reads are really longer, and the overlapping regions should be easier to find in some way. But the problem is that at least with nanopore, we have a higher value error, and that makes the things a bit more difficult in some way. With PacBio, we have a low error rates, so that works better. But yeah, it should be a little more lighter computationally than short-read assembly, but also have its own drawbacks in some way. But it's very common to do today long-read only assembly because it's gotten cheaper, especially with Nanocore,
Yeah.
and it's basically a very affordable way and easy to use
Yeah.
an onboard device.
Mikhail.
Yes, I have a question. Thank you for the presentation, Diego, and thank you for a nice tool. Um, I do not work that often with metagenomics data. I was using this pipeline a year ago, and I was very surprised now when you presented 5.1, because I think a year ago it was still 2.5, I think, I was working with. But I guess that you have been done a lot of job with the long read sequencing, and I have only been using short read sequencing. So one of my questions is, have you changed anything from the older versions like a year ago with the short read work?
Turn rates should be almost the same. We only have been organizing the processing modules because we're only with all very tied together. We designed right now a more modular way to organize them, but it should work basically the same. We only updated space to its latest version, but aside from that, it will be the assembly step should be exactly the same.
Okay, so no change of tools. Yeah, I need to start working with long reads. I know that. But do you have any recommendation, or have you been doing any benchmarking to see how much or the coverage or the depth of long read sequencing? Is it like one nanopore flongel cell? Does that help at all, or have you found like a minimum number of?
I don't have the numbers. We don't have. We have not been running a lot of benchmark recently. We have planned to do that at least for the full test. But I guess the amount of information should be around the same. I guess. I don't know. 10 gigabases per sample, something like that. So should work well for long reads.
And just one comment, the flongles have been discontinued, so you will not be able to run flongles anymore for ONT.
Yeah.
Yeah, I heard something about that. That's terrible. It's super good to have sometimes.
Could have come in very handy for some things, but yeah, unfortunately. Do you have any more questions?
No, not from me.
Okay, thank you so much. Are there any more questions from the audience?
Hi,
Yes.
Francisca and Diego. I have a question. I've worked with metagenomics before now, and I use the custom Python scripts for that. So I want to say thank you for giving us the NFCO package to be able to run it. But I have some concern I would like to discuss. Firstly, I don't know if hybrid spades tool is incorporated in the pipeline. This is one. And then secondly, if it is incorporated, the hybrid assembly, does it significantly improve the fragmented Illumina assemblies when perform the assembly?
Um, Hybrid assembly itself try to combine the advantage of both the best qualities of each technology. In the case of long reads, we have bigger reads, so it's more easy to form longer context. And in the case of Illumina, obviously, it's the quality. In general, I will say that hybrid assembly produce better quality genomes that only using either long reads or short reads. But it also depends how much depth do you have. But if you have only, for example, the same data, all the short reads, and the same data plus some long reads, it should work better.
Okay, thank you for your question. I mean, the main reason why I asked this question was, I think when I use hybrid spade to perform the assembly, I found out that some of the samples, only one sample actually improved, but the other samples which I ran without hybrid spade, I used just the long read mode to run it, did perform way more better. But when I tried to perform using the hybrid spade, those long reads didn't perform any more better again, and I'm really surprised why what happened. Maybe the pipeline, the custom script wasn't substantial enough, or maybe I really don't understand. So this is one of the reasons why I asked these questions to be able to
I see.
figure that out.
Um, if I have to think on something, maybe uh, it could be the level of error of nanopore.
Yeah.
Nanopore has been a lot of change recently,
Mhm.
so all nanopore reads have like 10% of error.
Mhm.
That's a lot. And recently we have like 3 or 2% in the common case. That
Mm.
is way better. And that could be a big factor in how the contexts are assembled and which sequence to decide a space hybrid to determine how to build the genomes.
Okay, thank you for your question. Thank you for your answer. Sorry. Thank you.
Thank you.
you for the questions. Do we have any more questions? No, I think then I would like to thank you very much for this great talk, and also the audience for listening in, and I hope to see you for our next bite-sized talk. Have a great day.
Thank you.
Thank you.
You too.